You know, when you really think about it, every single drop of water that exists in our world, as well as every delicate snowflake that gently falls from the sky and eventually melts away, is much more than just a simple part of nature. Each one of these tiny elements actually holds within it a small but significant bundle of energy. This energy is stored in the bonds between the molecules that make up the water, and when a snowflake. It carries the potential to join together, to flow, to fall, to pull, to push. These bundles of energy come together if they land in the right place. At first, they flow in thin ribbons, little streams, brooks, creeks, and finally rivers. People realized long ago just how much power is hidden in flowing water and how much energy it can give us if we manage to harness it. The slopes of the low Tatras are vast enough. They are covered with rich forests capable of storing plenty of water, and they are also shaped by the land in such a way that they can supply the Železiarne Valley year-round with springs that never dry up and always have enough water. The local inhabitants realized a long time ago just how much wealth is hidden in the streams and rivers flowing down from the slopes. They harnessed their energy with dams and directed the water into sawmills, mills, and other ingenious devices that helped them saw wood, grind grain, forge, and power machines. The Železiarne region has a rich tradition of metallurgical production. The ores that were mined beneath the surrounding hills began to be processed here as early as the 14th century. At first, these were just cast iron products and smaller iron items. Later, in the 16th and 17th centuries, Železiarne experienced an unprecedented boom in iron production, with its products primarily supplying the surrounding mining and metallurgical industries. In the 18th century, the so-called Frančanski complex was established around the upper reaches of the Rhone River, becoming the most important center for iron production in the entire Austro-Hungarian Empire. And finally, in 1840, at the foot of Podbrezová mountain, construction began on a large ironworks and rolling mill, which would later produce the highest quality rails in Europe for the rapidly expanding railway transport. A factory is successful, so it expands, modernizes its technology, and produces a variety of metallurgical, rolled, and forged products. The ironworks need more and more energy. Almost until the end of the 19th century, the factory in Podbrezová uses exclusively wood and charcoal to produce iron, but there is less and less of it in the surrounding area. For processing iron, they rely solely on energy from the Rhone River and its local tributaries. However, major metallurgical companies around the world are already using a different kind of energy in production, electricity. To stay competitive, the factory starts to implement it as well. At the beginning of the 20th century, the factory management decides to harness the energy potential of the local streams for electricity production. That's why, in 1903, an energy complex of weirs, collection channels, water tanks, reservoirs, and power plants begins to take shape around Podbrezova. At that time, it was unique, and even today, it remains exceptional and fully operational in Slovakia.
I'm not a metallurgist, but I think the melting point of iron is somewhere around 1,600 to 1,650 degrees Celsius.
For every metallurgical plant or company producing liquid steel or other secondary metallurgical products, electricity, as the most fundamental form of energy, is basically like the lifeblood of the human body.
The average consumption of electricity to melt or produce 1 ton of steel is approximately 480 kilowatt hours.
We are among the 10 largest consumers of energy, whether it's electricity or natural gas. In Slovakia, we consume more than 250,000 megawatt hours of electricity annually, and in natural gas, almost 500,000 megawatt hours per year.
Electricity is, of course, used to provide for the basic activities, so that we have lighting in the premises, so that we have, I don't know, the functionality, let's say, of everyday life in the steelworks or in the company, in administrative buildings, but mainly it is used to power technological units, production, and manufacturing technology. And the most significant or the largest consumption of electricity here in the steelworks is actually for steel production.
Today, we can't even imagine factories operating without electricity. Similarly, we can't imagine today's builders and engineers working without sophisticated electronic devices. At the beginning of the 20th century, back in the days of the former Austro-Hungarian Empire, when the construction of small hydroelectric power plants for the then ironworks began, their creators had only the simplest tools at their disposal. Despite that, they created a technical work that still serves its purpose to this day. Its design is based on diverting the waters of local streams into weirs, collection channels, and reservoirs from which the individual power plants are supplied.
But these power plants, when processing water, use or take advantage of all those mountain streams. So it's not just one stream, but a combination of these streams that flows through these power plants.
This water practically passes through all the power plants and generates electricity. So it's a good use of the water's potential.
The water that flows during the day, at night, in summer, in winter, it's always available, and basically, that's the principle on which the main production of electricity was built.
One of the preserved power plants is a small hydroelectric power plant. Paisak is an unassuming building hidden within the grounds of the former machine works. It was built between 1903 and 1908. The permit for its operation was issued by the then county office in Banska Bystrica in January 1908. Its builders used water from the Stajovnica stream, where they constructed a dam with 2 sluice gates. One gate regulates the water supply to the artificial channel, and the second is a bypass sluice with an opening to ensure a minimum flow in the watercourse. From the dam, water is brought by a surface artificial channel to the Bystrianka stream, all the way to the dam in Bystra. Its length is approximately 710 meters. Up to 8 cubic meters of water per second flow through the channel. When the water reaches the dam, it is stopped by a circular sluice gate at the entrance to the underground channel, which is equipped with grates to catch debris. These need to be constantly removed to ensure a steady flow of water through them. The most important thing in generating electricity at hydroelectric power plants is to have enough water, which means making sure that the reservoirs and dams are kept clean, that the grates are maintained and clear of debris, so that we can get the maximum amount of water to the turbines and they can generate electricity. An ordinary person might not even realize that the stream disappears at the dam, vanishing into an underground reinforced concrete channel with a diameter of 1,750 millimeters. Part of the water flows away through a spillway channel, but as much as 4 cubic meters of water per second travels along the contour of the hillside for 4,700 meters to the sedimentation reservoir called Deal, which is located 72 meters above the Paisak hydroelectric power plant. To reach the spot where the water enters the reservoir, we first have to cross a 120-meter long reinforced concrete pool with a water depth of 2.5 meters. Those who aren't in the know have no idea what's hidden behind the unassuming little house on the hillside. It's a strange feeling to walk through places where time seems to have stood still for over 100 years. Over that time, the place has developed its own unique atmosphere and lives a life of its own. In the past, the facility had staff on duty at all times. Today, it is operated automatically. A remotely controlled machine now cleans the numbers. A worker only comes by occasionally to check on things and to clean the water from any sediment. During the visit, they also check above the upper part of the reservoir to make sure the water intake for the old plant is working properly. The water flows out of the reservoir through a discharge structure. It passes through fine screens with a cleaning machine. A hydraulically self-lowering sluice gate serves as an emergency shutoff. Once the water is cleared of coarse debris as well as finer suspended matter, it flows through a steel pipe with a diameter of 1,200 millimeters, which is buried underground leading to the power plant turbines. Down in the lower part near the turbines, its pressure increases to 7 bars. I wonder how the first employees in this building felt when the brand new turbines spun for the first time and the first electricity lit up the bulbs. Everything was new and completely different from before. The roar of steam engines was replaced by the monotonous sound of electric ones. The operators were no longer at risk of burns, but of electric shock. But it's easy to get used to something better, and after initial training, the employees quickly mastered the new technology. When we look at these machines, we might feel a bit nostalgic for the old days. It's as if back then, manufacturers cared more about the appearance of the equipment. And maybe it's just because more things were made by hand, but none of the power plant's equipment today is original anymore. The two Francis turbines date all the way back to 1928. Unfortunately, we no longer know the reason for the replacement. The smaller of the turbines has an output of 435 kilowatts, and at full power, as much as 800 liters of water flow through it every second. The larger one operates at 810 kilowatts with a flow rate of 1,600 liters of water per second. The turbines drive generators with an installed capacity of 670 and 1,350 kilovolt amperes. Both produce a voltage of 6,300 volts at 1,000 revolutions per minute. Keeping the power plant operational means taking care of everything that works and replacing anything unsuitable with something new. But it's not that simple.
Some things were scrapped, new ones were built, and some had to be rebuilt into a modern system. I remember, for example, the switches with a large amount of oil. Those switches contained 200, 300, even 400 liters of oil. If that caught fire because of a short circuit, it would ignite in such a way that it couldn't be put out. It just wasn't possible to maintain, so they were replaced. New ones were made. With air, with expansion, and so on. Basically, all these devices were modernized. That's why these hydroelectric power plants have remained, even to this day, because they had to be rebuilt.
Not everything is described in the documentation the way we're used to, or like with new equipment, where there are technical reports. We dismantle parts of the equipment and basically approach the repair in such a way that we look for or examine how it was made, how to replace it, or how to restore it to its original condition. Here, it's pretty important to draw knowledge from predecessors, from older people who worked at the power plants, and today it's hard to put together some kind of operating manual that says, run it like this, maintain it like that. The staff needs to have a kind of craftsmanship when it comes to maintenance, so they can handle these, let's say, atypical or custom-made devices, and keep them in a state or condition where they can continue to operate, such as for extended periods.
All efforts are aimed at one thing: to produce electric power in the power plants. Each power plant has its own substation, through which it sends electricity to the factory. A prerequisite for the proper functioning of the power plant is to ensure that the turbines have enough clean water. In the basement, workers monitor its condition. It must be free of all debris that could damage the turbine blades. From the power plant, the treated water is also sent to the main factory. In these areas, there are also automatic valves for shutting off the water supply to the turbines. Water used to cool the turbine bearings is brought here, and through the largest pipes flows the water leaving the turbines. This water flows out of the power plant back into the Bystricky stream, just as it did over 100 years ago. But not everything in the power plant system has stayed the same.
At the beginning of the hydroelectric plants, at the start of electrification, the entire ironworks factory, the whole cooperative, was supplied by its own power plants. There was an installed capacity of about 5 megawatts, 5 or 6 megawatts. Later, this was reduced because 2 power plants were shut down. One of them was the Lopesca plant, and it had about 600 kilowatts. The supply channel was an obstacle to the development of road infrastructure. Similarly, the hydroelectric plant located directly in the Podbrezová ironworks was also an obstacle to the company's development. That one was also dismantled after the front passed through.
The factory changed, the steel processing technologies changed too, but the principle of harnessing energy from water has remained the same for centuries. First, the water needs to be captured and directed to one place so that enough of it accumulates to continuously supply the turbines. Its inflow must be sufficient to replace the amount of water that is taken out. Look at the streams running through the long valleys of the low Tatras. These are the places where the initial accumulation of water takes place. With sluice gates on the dam, the water level is raised, and the water is directed through screens where it is cleared of coarse debris, then guided into the reservoir. In the case of this dam, a channel with an internal diameter of 900 millimeters and a length of 4 kilometers runs along the contour of the hills to the Rigel Reservoir, but more on that later. The same process happens at the Bielvadi Dam. A power plant worker regularly checks and cleans it, especially after spring floods, storms, and heavy rains, when the trash racks are often full of debris. From the Bielvadi Dam, a channel with an internal diameter of 900 millimeters has been built, which, after 1 kilometer, leads to the Pavkova Dam. Here, the water from the channel merges with the waters from the Prostredny and Guelphav streams. The dam directs the water into an 8-kilometer-long tunnel with an internal diameter of 1,000 millimeters, which leads it to the Rigel Reservoir. The dam also serves to settle fine sediments, which, in fast-flowing water, have abrasive effects. To prevent the dam from getting clogged with them, a worker has to occasionally open it and flush it out with a stream of water. Only then can you see the incoming water from the dam of the white water. and also the inlet into the canal leading to the Rigel water reservoir. I walk with the power plant worker along the canal, which winds its way down the hillside above the valley at a 0.7% slope. It was built using mining methods, blasting with dynamite below the surface, and reportedly, prisoners of war from World War I also helped with its construction. Digging tunnels in the rocky ground was no small feat, no wonder that 2 companies at the time went bankrupt because of it. To build 2 supply channels in that mountainous, rocky terrain. With the means they had back then, using dynamite. Without any heavy machinery, I really admire those people. There is an entrance to the channel approximately every kilometer. A system of troughs brings water from the surrounding streams into them. If the channel gets overloaded, the water doesn't flow out. They need to be cleaned regularly. A grate catches large debris. Fine sediments settle in the sedimentation shaft. During the winter, fire salamanders find shelter in them. Sometimes, at the beginning of spring, a worker discovers dozens of them here. The entire structure fits perfectly into nature and has hardly needed any maintenance to this day. Hopefully, it will keep working like this for another century. But for it to function, there must be a healthy forest around it, capable of absorbing enough water. And a healthy forest also means an abundance of life. The water works, as if a protective hand was watching over it. The Rigel Accumulation Reservoir is located at an altitude of almost 730 meters above sea level, about 200 meters above the Jasony power plant. At the end of the war, soldiers wanted to destroy it, but the shots left almost no marks on the high-quality concrete. No wonder, since it had to be built to hold about 9,000 cubic meters of water, which it is capable of accumulating. The internal dimensions of the structure are impressive. Beneath the surface, there are concrete chambers on both sides. The left chamber, into which water flows from the Bavkova weir, is 90 meters long, 10 meters wide, and 6 meters deep. The right chamber is 40 meters longer. Water from the Lomnista weir flows into it. The central chamber, which is the only one we can see, is 19 meters long, 10 meters deep, and 20 meters wide. When we go below the level of the pools, we pass by the now non-operational elevator engine room into the area of the special safety shutoff, which closes the water supply in case of a pipe failure. Even this device, with only minimal maintenance, has been working reliably for almost 100 years. But the elevator is now just a museum exhibit. It hasn't been used for years. Its operation was inefficient. The massive forged pipeline leads from the accumulation tank, through the safety valve and the reservoir walls, all the way to the power plant. It is 900 meters long, and at the bottom section, it has to withstand a pressure of 20 bars. When the Germans tried to destroy it at the end of the war, water supposedly shot up to 30 meters high through the bullet hole. The pipeline's expansion is managed by telescopically sliding sections. The elevator rails will probably be gradually reclaimed by nature. When the turbines in the power plant are out of operation or the water level in the storage reservoir exceeds the maximum limit, the excess water is automatically redirected to the spillway, which carries it down into the valley. This can also be done manually using discharge valves. And in the past, this was done by the reservoir operators. Today, even this is controlled automatically. How much water has flowed through this pipeline in 91 years of operation, and how much more will flow through it? You probably wouldn't guess that such a beautiful little house hides a power plant. In the past, employees used to live here as well. It was built between 1922 and 1924 during the construction of the entire power plant. But it's not just the exterior that's amazing. The interior will enchant any technology enthusiast.
When I first came to the power plant, when I started working at the ironworks, I ended up at the power plant in Jacine. I felt like I had walked into a museum. The equipment, those generators, the look and condition of everything made such an impression on me. A technical monument, but still operational.
And it continues to work. The employees keep the power plant running with just routine inspections and regular maintenance repairs. Pressurized water from the pipeline flows to the turbines through 3 branches. 2 of them lead the water to the 2 main Pelton turbines. The 3rd branch directs water to a pair of small Pelton turbines, which drive the exciter dynamos used to energize the electromagnetic poles of the synchronous generator rotors. The main turbines utilize the hydroenergetic potential of the water column, meaning the height difference between the level in the storage reservoir and the turbines. That is 196 meters. The output of the turbine is proportional to the head and the amount of water flowing through it. With turbines, there is an inverse relationship. The higher the water column above the turbine, the less water the turbine needs per unit of output. Each turbine is unique. You could say it is custom-made. The ones here have outputs of 810 and 1,620 kilowatts and spin at a speed of 500 revolutions per minute. They only need 1.5 cubic meters of water per second to achieve this feat. They also drive massive flywheels that keep the whole system running smoothly. The turbine shafts set in motion generators with a total output of 2,340 kilowatts. The small hydroelectric power plant in Jacine began construction in 1922. A large part of the documentation was lost during the war. Only a portion of the construction logs has been preserved. They contain only bare facts: when, what, and how much was used, what work was done, and how many people worked on the construction on a given day. What? Feelings people experienced as something new was rising before their eyes. We cannot learn from them. There are no more witnesses left to reminisce. Only a few photographs remain. What matters is that the power plant served its purpose and still does to this day. The equipment works. Operators have come and gone. Over the years, the space has become lived in, familiar, and well-trodden. Who knows how many times these machines have been cleaned, how many times they've been taken apart and put back together. Who adjusted them, changed the carbon brushes, cleaned the contacts. The machines don't answer, they just hum and diligently do what they're meant to do. Today we live in a time when things tend to work only for a very short while. So how is it that these have been working for almost 100 years?
They were probably well made back then. Those who invented and built them did an honest job. And of course, proper care as well. These have been maintained for generations by people who look after them, keeping them in operation so they can continue to function.
The water has done its job and moves on. At the time when the Železiarne power plant was built, there were still other users of the stream's water power. There were 4 mills and 1 sawmill operating on it. Since the Železiarne power plant can operate in peak mode, it was only natural that the owners wanted the water flow to be constant. In 1938, the ironworks therefore built an equalizing reservoir with a capacity of about 10,000 cubic meters below the power plant. Right after the pond was built, there were already considerations about how to use the energy it represented. These ideas were only realized in 1998, when the equalizing reservoir was repaired. Another small hydroelectric power plant in the system was put into operation in the middle of 1999. It is located 4.5 meters below the level of the equalizing reservoir. A Kaplan-type turbine with a total output of 78 kilowatts is installed in it. 2.6 cubic meters of water flow through it every second. The water continues to flow and still carries energy. At the Podbrezová ironworks, they have always taken a very pragmatic approach to energy.
Electricity is actually a commodity that's traded on European exchanges just like any other form of energy. And of course, there are also additional so-called network fees associated with it, which we also have to pay, even if we generate this electricity ourselves. There are also other so-called network fees associated with it, which we also have to pay, even if we generate this electricity ourselves. But whenever a company produces its own electricity, it is definitely more economically efficient than buying electricity from other companies.
That's also why the ironworks aim to take advantage of the potential of all the water sources available in the area. That's why a weir was built on the Ron River below the former Lopez hydroelectric plant, which diverted part of the river through a canal to the confluence of the Vojkovsky stream and the Ron. Another weir was built, which directs water into the so-called Lopez Canal, a tunnel conduit that once connected the Lopez hydroelectric plant with the one in Dubova. Before entering the canal, the water first passes through coarse screens into a settling tank, and from there it goes through finer screens with a cleaning machine. After that, it disappears into an underground canal, which leads to another small hydroelectric power plant in the village of Podbrezová. However, that plant does not use water from the canal. Its source of energy is the Jasinski stream, whose waters had already been used once by the Jasinska power plant. But water doesn't just bring energy with it. Opponents of small hydroelectric power plants often don't realize when criticizing them that it's actually thanks to these plants that rivers are cleared of large debris, especially after storms. When the water levels of streams and rivers rise, debris is filtered out at the power plant, sometimes even tens of tons of plastics and other waste that people have dumped at illegal landfills near the rivers. Even this debris sometimes needs to be cleared of finer inorganic sediments by opening the sluice gates. The cleaned water enters the turbines, which utilize the energy potential from the increased inflow of water from the Jasinski stream into the tunnel feeder for the Dubova hydroelectric power plant, running beneath the power station. In the past, the water used to fall into it without being put to any use. The energy from the 7.7-meter drop of water was only harnessed in 1998 when the power plant was put into operation. The hydroelectric power plant is unattended. Employees only come by occasionally to check if everything is in order. The plant operates with 2 Francis turbines. Both are powered by 3-phase motors, which function as generators. The smaller one has an output of 80 kilowatts, and its generator produces 75. The larger one has twice the output, as does the generator it drives. The turbines are from the same manufacturer as the turbines in the Jasony power plant, from KD Blansko. So it's possible to compare how much the technology has advanced over the years. Everything seems to have become lighter and simpler. Functionality has replaced beauty. Safety and automation now dominate the equipment. They are more efficient and more advanced. Beneath the power plant, there is a so-called calming pool, where not only the water from the turbines flows, but also, in the event of a shutdown or malfunction of the plant, water from the pipe that serves as an overflow channel. Finally, the water from the pool flows into a canal conduit, which runs underground for about 2,100 meters all the way to the Dubova hydroelectric power plant. So, the canal ends at a small house with an observation post, from which they used to report to the power plant when a storm was approaching. The power plant always had to prepare for that. More than 9.5 cubic meters of water flow through the canal every second. But before it enters the steel pipe with a diameter of 2 meters to spin the turbines, it still passes through fine screens with an automatic cleaning system to remove debris. If the turbines at the power plant are out of operation, the water automatically starts flowing through a remote spillway into the Ron River. That's when you can really realize how powerful it is. The Dubova power plant is located 23.5 meters below the outlet of the feeder channel. Its construction began in 1902 and was completed in 1909. When we step inside, our first impression is that we've traveled back in time more than 100 years. The power plant was originally equipped with 2 Francis turbines, each with a flow rate of 3 cubic meters of water per second and an output of 553 kilowatts. When the power plant was renovated in 1975 and the original control panel was replaced with a modern one, the old marble panel was offered to the Technical Museum. It rejected the offer. Fortunately, the management of the steelworks decided to preserve it, and today it serves as a unique backdrop for the equipment on the power plant stage. The original turbine still operates flawlessly to this day. Together with the monumental exciter and the old generator, whose output is 750 kilovolt amperes. At 387 revolutions per minute, it produces a voltage of 6,300 volts. The second turbine was replaced in 1975 by a Kaplan turbine from 1938 with an output of 1,260 kilowatts, which the factory acquired from a decommissioned power plant in Banska Bystrica. First, in 1982, it was converted into a Kaplan propeller turbine, and finally, during the reconstruction of the Lopez-Tabova supply channel, it was transported to KD Blansko, where it was modified so that its highest efficiency would be at 800 kilowatts. Today, its maximum output is 970 kilowatts, and it can handle up to 6 cubic meters of water per second. What most distinguishes modern power plants from the original ones is the electronic control and automation of the entire operation. Both the workers and the management of the plant have real-time information about the current status of every section and piece of equipment. The water from the slopes of the low Tatras completes its final task by flowing through the power plants and then drains into the Ron River via the canal. It spun 11 turbines with an installed capacity of 5,374 kilowatts and produced 30 million kilowatt hours of electricity per year. It's not enough just to generate electricity.
A power plant by itself, that's not much. There are other components between the power plants and the steel factory. Connecting routes, substations, and wiring throughout the factory. All of that is part of supplying electricity to the steel plant.
Each power plant produces a different amount of electricity with different parameters. In substations, transformers convert the generated voltage and current to values suitable for transmission. This is carried out through 22 kilovolt lines all the way to the main substation at the plant, maintaining. Long-distance power lines requires quite a bit of effort. They have to operate in every season, under all weather conditions. All the electricity ends up at the main substation. both the electricity produced and the electricity purchased from distribution networks. Here, in what you could call the heart of the entire steelworks, the electricity is distributed to the individual operations. Železiarne Podbrezová successfully competes with global metallurgical companies, not only with high-quality products. There's something else behind it as well.
Our biggest competitors are mostly companies in Western Europe. And I can say that no competing company has as high a share of its own electricity production in its total consumption as we do. This means that it is dependent on purchasing from other manufacturers.
At the factory, they never underestimated the importance of producing their own electricity. But with just small hydroelectric plants, they would never be able to significantly cover the plant's energy consumption. That's also why, in 2001, the Podbrezová Steelworks decided to invest in developing additional in-house energy sources. In the building of the former boiler house of the new plant, they built a combined cycle gas turbine facility for producing electricity and medium pressure steam. The heart of the combined cycle plant is a gas combustion turbine and a waste heat boiler. The turbine drives a generator with an electrical output of 4,454 kilowatts. The energy from the outgoing hot exhaust gases is further utilized in the medium pressure steam boiler. Its inlets and outlets are connected to the original piping of the old boiler house. To improve the utilization of the produced steam, especially during the summer months, a small steam turbine was additionally installed at the turn of 2010 and 2011, which drives a generator with an output of 260 kilowatts. Over the past 100 years, electricity generation technologies have undergone tremendous development. How is it possible that in the Podbrezová ironworks, the old technology is still operating right alongside the new one?
We have always considered ourselves a conservative company. Many times, we haven't followed fashionable trends, and that's still true today. So, because we've always said that what you have at home counts, our previous generations have always operated these facilities after they were built. Well, we, who joined this company in the 1970s, have continued this work. And even after the change in political conditions in Slovakia, we can say that we have done very well, that we are still repairing, operating, and modernizing our equipment. And now,
And this also shows that we produce about a quarter of the electricity we consume ourselves at home.
At the Železiarne power plant, the turbine is spinning up once again. Together with the flywheel and generator, it's picking up speed. Just like almost 100 years ago, the operator regulates them manually. He fine-tunes, monitors the control instruments, and especially keeps an eye on the light bulb. When it goes out, it means the electricity produced and the electricity in the grid are synchronized. The energy converted from water can now start to serve its purpose. If a person creates something meaningful, it endures for ages and brings benefit to many for a long time. But it's also important to know how to appreciate those truly meaningful things, to take care of them, to improve them, and to build upon them. The oldest of the power plants at the Podbrezová ironworks have been operating for over 100 years. Many people have taken turns operating and maintaining them. They tied their lives to them. They served them faithfully. They devoted most of their life's energy to them, so that in turn, the plants could reliably serve others. The part of their lives they invested in them is a commitment for future generations as well, so that they continue to take good care of the power plants, as well as the other facilities that bring jobs to the whole region, allow people to live here, and help them maintain their pride in their homeland.